Welcome to the deep dive. Today, we're not just scratching the surface. We're really drilling down deep into how artificial intelligence is, well, completely changing the landscape of geology.
It really is.
You sent over this fantastic resource, artificialintelligencegeology.pdf, and our mission today is basically to unearth the most mind-blowing, the most impactful ways AI is helping us understand our planet, from its core right out to the crust.
That's a good way to put it.
Get ready to see Earth science through like a totally new AI-powered lens. It's revealing insights that honestly traditional methods often miss. Some of this stuff is truly game-changing.
Absolutely. And that document you mentioned, artificialintelligencegeology.pdf by Mohammed Midhat Gaber,
Right.
it gives a really solid, comprehensive framework for understanding this whole revolution.
Right.
It takes you from the real fundamentals of AI right through to the cutting-edge applications we're seeing now in geological research. It's actually a great way to grasp not just what's happening now, but where the field is heading.
Yeah, exactly. And for you, the learner listening in, you want to get smart on important topics quickly, right? You love those aha moments, but maybe without feeling totally overwhelmed. Well, this deep dive is tailored just for you. We're going to break down these sometimes complex ideas into clear, digestible insights. We'll spotlight the truly surprising stuff and always focus on, why it matters to you.
Makes sense.
So before we jump fully into the AI magic, let's maybe set the stage a bit. Using computers in geology, that's not exactly a brand new idea, is it? Where did this whole computational journey begin?
That's right. That's got quite a history. Early on, geologists started using regression analysis. Pretty foundational stuff, exploring relationships in geological data, seeing how different factors influence each other.
Okay.
Then came geostatistics. That allowed for much more sophisticated analysis of spatial data, absolutely crucial for things like mapping out mineral resources, understanding variations across areas.
Right. Spatial stuff is key in geology.
Definitely. And then modeling software emerged, letting us simulate complex geological processes. Think about simulating how mountains form or how rivers change course.
Right.
And of course, GIS, geographic information systems. That really transformed how we handle and visualize spatial information. It completely revolutionized geological mapping. So yeah, these were the essential building blocks, the groundwork that really paved the way for the AI revolution we're talking about now.
Okay, so those were the original tools in the geologist's computational toolbox. But what were their limits? Why did we need this big leap forward into AI? What problems could AI solve that those earlier methods just couldn't handle effectively?
Yeah, good question. The shift towards AI was really driven by a few key factors. First, just the sheer volume of geological data absolutely exploded.
Right.
Think about the massive data sets coming from things like advanced seismic imaging or global satellite networks monitoring the Earth 2037. It just became, well, almost impossible for traditional methods to process and interpret all of that effectively.
Too much information.
Exactly. Second, AI turned out to be incredibly good at finding really subtle patterns and correlations within all this complex data. Patterns that honestly would often just be completely missed by conventional analysis.
Seeing the unseen connections.
Precisely. Automation was another huge driver. AI offered the potential to automate so many of those repetitive, time-consuming tasks in data processing and analysis. That frees up geologists to focus on the bigger picture, the more interpretive questions.
Makes sense. Let the machines do the grunt work.
Right. And finally, AI has really delivered on its promise of significantly improved predictive capabilities. Whether it's predicting where valuable resources might be hidden or forecasting geological hazards like earthquakes or landslides with much greater accuracy than before.
Okay, so AI steps in as this ultimate geological data detective, crunching massive amounts of data, finding hidden patterns, automating tasks, and making better predictions. Now, when we say AI, it's obviously a huge field. What are the specific branches of AI that are really making waves in geology right now? What are the key tools in this modern AI geologist's kit?
Yeah, it helps to think of it like a specialized toolkit. First up, you have machine learning, ML. That's fantastic for building predictive models, classifying different geological features, and just generally making sense of really complex data sets.
Okay, ML is kind of the workhorse.
It often is. And within that, you have deep learning, which uses these powerful multi-layered neural networks. It's absolutely essential for tasks like analyzing complex seismic data, interpreting geological imagery, and automatically pulling out important features from that data.
So deep learning is like ML on steroids, especially for complex patterns.
Kind of, yeah. especially for perceptual tasks like image or signal analysis. Then there's computer vision, which focuses specifically on analyzing visual information, think images from satellites, drones, even down to microscopes looking at rock slices. It's used for detailed mapping and identifying geological structures.
Got it. Analyzing the pictures.
Exactly. Then natural language processing, NLP. This is fascinating. It helps us extract valuable insights from the huge amount of written text out there, like geological reports, research papers, field notes.
So reading the research for us.
In a way, yeah, pulling out key information. We also have robotics and automation. These are increasingly being used for things like autonomous data collection, sending robots or drones into environments that are maybe too dangerous or difficult for humans.
Like exploring deep sea vents or something.
Potentially, yes, or mapping hazardous mine areas. And finally, you have expert systems. These try to mimic the reasoning process of human geological experts to help with decision-making, especially in complex areas like resource exploration where you need to weigh lots of factors.
Wow, that's a really powerful set of tools. So how are these different AI techniques actually changing the day-to-day work of geologists? What's the real-world impact on geological practices?
Well, the impact is truly transformative. It's not an exaggeration. One major area is just enhanced data analysis and interpretation. Like we said, AI algorithms can sift through these enormous data sets.
They have data explosion.
Right. And they can uncover really subtle relationships and correlations that traditional analysis might completely miss. This just leads to much more informed, more nuanced understandings of geological processes.
Deeper insights from the data.
Exactly. And secondly, AI is significantly boosting our ability to build more accurate predictive models. This applies across the board, predicting resource locations, forecasting natural hazards like landslides or volcanic eruptions. The models are just getting better.
Right, so we're getting deeper insights and more accurate forecasts. What about the really practical side of things, like, actually finding resources or getting them out of the ground? How is AI changing exploration and mining?
Oh, absolutely. AI is revolutionizing exploration and mining in several key ways. For one, we're seeing the rise of automated exploration. You've got AI-powered drones and robots that can conduct surveys, maybe even collect samples in really remote or hazardous areas.
So safer and maybe faster exploration.
Safer and often more efficient, yeah. Then there's predictive maintenance in mining operations. AI analyzes sensor data from heavy equipment.
Like the big trucks and drills.
Exactly. And it predicts when a piece of equipment might fail before it happens. That minimizes costly downtime and improves safety.
That makes a lot of sense.
AI is also being used to optimize the actual resource extraction techniques, helping figure out the best way to mine or drill to maximize the amount of valuable material recovered, while, importantly, minimizing the environmental impact.
Okay. Efficiency and environmental consideration.
And crucially, AI is playing a bigger and bigger role in improving worker safety in hazardous environments like mines. By continuously monitoring conditions, air quality, ground stability, and identifying potential risks in real time.
That's fantastic, especially the safety aspect. It's not just about finding more stuff or being more efficient. It's actually about protecting people.
Absolutely critical.
What about the bigger picture then? How does AI in geology connect with broader environmental issues and, sustainability?
Yeah, this is a really critical link and a positive one. AI offers significant opportunities for positive environmental impact. It can help optimize resource use, leading to less waste and better conservation practices.
Using resources more wisely?
Exactly. AI-powered systems are also being deployed for environmental monitoring, tracking changes in ecosystems, maybe related to mining or other geological activities, much more effectively.
Right.
In the context of natural disasters, AI can provide much earlier warnings for events like landslides or floods, based on analyzing sensor data and predictive models. That can potentially save lives and reduce damage significantly.
Early warnings are huge.
Huge. And more broadly, AI is contributing to the development of more sustainable resource extraction practices overall, helping to make the geological sciences, which are inherently about resource use, more environmentally responsible.
So it seems like from the tiniest microscopic detail to the massive planetary scale, AI is making waves across geology. Let's maybe zoom in on some specific examples now. The book excerpt talks quite a bit about supervised learning. How is that actually used in practice? For instance, how does it help identify different types of rocks and minerals?
Right. Supervised learning, where the AI learns from data that's already been labeled by humans, is proving incredibly effective for these kinds of identification tasks. Take rock and mineral ID. We use things called convolutional neural networks, or CNNs.
CNNs, okay. Heard of those in image recognition.
Exactly the same principle. They're trained on huge collections of images. Could be close-ups of hand samples, could be microscopic views of thin rock slices, even photos of large outcrops in the field.
A massive photo library for rocks.
Pretty much. And these CNNs learn to automatically recognize the visual patterns, the textures, the structures, and classify the samples really quickly and accurately. The key, though, is having a massive amount of diverse training data.
These lots of examples to learn from.
Precisely. And we even use techniques to artificially expand the data, like rotating images or changing the lighting to make the models even more robust. It's essentially like giving a computer expert-level visual recognition skills, but specifically for geological materials.
Wow. That's like giving a computer a superpowered geologist's eye. Okay, but what if we can't physically get our hands on a sample? How does AI help identify minerals remotely, say from an airplane or even a satellite way up in space?
Yeah, that's where spectral analysis combined with AI comes in. It's really cool. Different minerals reflect and absorb light in unique ways across the electromagnetic spectrum, visible light, infrared, etc., with distinct spectral fingerprints.
Like a barcode made of light.
That's a great analogy. So AI algorithms can analyze this spectral data, which might be collected by instruments you carry in the field. Or, more excitingly, from remote sensing platforms, satellites, aircraft-mounted sensors.
Okay.
We train AI models on the known spectral signatures of different minerals. Then we feed the AI new spectral data from a target area, and it can identify the likely mineral composition on the ground, even if it's a completely inaccessible mountain range or desert.
That is incredible. So we can essentially see the mineral makeup of the Earth from space using AI. What about the materials closer to the surface, like classifying soils and sediments? How is AI being applied there?
Classifying soils and sediments based on their properties, physical, chemical, is really important for lots of things. Think agriculture, construction safety, environmental risk assessment.
Right, knowing what the ground is made of.
Exactly. So AI models can be trained on data that includes things like particle size distribution, soil texture, color, organic matter content, chemical composition, pH, all sorts of measurements.
Lots of inputs.
Yeah. And once trained, these models can quickly and accurately classify new soil or sediment samples. This helps with practical things like determining which crops will grow best in a certain soil, assessing if the ground is stable enough for building foundations, or identifying areas that might have potential soil contamination.
Okay, so supervised learning is great for identifying what something is, rock type, mineral, soil class. But what about when we want to measure how much of a property there is? Like, how much fluid a rock can hold porosity, or how easily fluids can flow through it, permeability. That sounds more like regression analysis, right?
Exactly right. Regression analysis, where the AI models learn to predict continuous numerical values instead of just categories, is absolutely crucial for quantifying these important geological properties.
Measuring things.
Precisely. In reservoir characterization, for example, that's understanding underground formations that might hold oil, gas, or water. AI algorithms analyze well log data. Those are measurements taken down boreholes.
The instruments they lower down the wells.
Exactly. They combine that with physical measurements from core samples retrieved from the wells. And from all that data, the AI learns to predict crucial parameters like porosity and permeability throughout the reservoir.
And why are those two so important?
Well, porosity tells you how much space there is in the rock to hold fluids, and permeability tells you how connected those spaces are, how easily the fluids can flow. These predictions directly inform huge decisions, like where exactly to drill new wells and how to best design the extraction process to recover the resources efficiently.
So it's not just about finding the oil and gas reservoir, it's about understanding its plumbing, basically, to get the resources out effectively.
That's a great way to think about it, yes.
What other reservoir characteristics can AI help predict using regression?
Oh, its capabilities extend quite far. AI can also predict the saturation levels of different fluids, how much oil versus gas versus water is present in the pore spaces. It can predict reservoir pressure and temperature, which are also critical for production. And it can even help predict the distribution of different rock types within the reservoir, what we call lithophases. Putting all that together gives you a much more comprehensive picture for managing these valuable resources.
Okay, and moving beyond just oil and gas reservoirs, how is regression analysis helping us understand the ground for other critical purposes, like ensuring the safety of big construction projects?
Yeah, in geotechnical engineering, the branch focused on the ground's mechanical properties, AI models are becoming really valuable. They're used to predict important parameters like shear strength,
Rojo.
basically how much stress a soil or rock can withstand before it fails, like in a landslide. And also the elastic modulus, which is a measure of its stiffness or resistance to deformation.
Okay, crucial for building things on top.
Absolutely vital. These predictions are essential for the safe design of foundations for buildings, bridges, dams, also for assessing the stability of slopes along highways or railways, and for designing tunnels safely. You need to know how the ground will behave under load, and AI helps predict that more accurately using available site data.
It really sounds like AI, through both classification and regression, is becoming an absolutely essential tool for just fundamentally understanding the physical properties of the earth beneath our feet.
It really is.
Now, let's shift gears slightly and talk about finding those resources that are hidden deep beneath the surface. How is AI being used for predictive modeling, specifically in the search for mineral deposits and maybe hydrocarbon reserves? You used the analogy earlier, finding a needle in a very large haystack.
That's a perfect analogy, and AI is helping us shrink the haystack, so to speak. In mineral deposit modeling, AI excels at integrating a huge variety, a real diversity of spatial data.
Like what kind of data?
Geological maps showing rock types and structures, geochemical surveys measuring element concentrations in soil or stream sediments, geophysical measurements like magnetism or gravity, even remote sensing data from satellites looking for alteration patterns.
Okay, pulling everything together.
Everything. AI algorithms, often machine learning models, process all this layered information to generate what are called mineral prospectivity or favorability maps. These maps essentially highlight the geographic areas with the highest statistical probability of hosting the type of mineral deposit you're looking for.
So it points the exploration teams in the right direction.
Exactly. It dramatically improves the efficiency of exploration efforts and significantly reduces costs because you can focus your expensive drilling programs on the most promising high-potential zones identified by the AI.
Right. Instead of just drilling somewhat randomly or based only on simpler models, you use AI to really target the areas where success is most likely. What about looking for oil and gas? Is it a similar AI-driven approach?
Yes, it follows a very similar principle, although the specific data types are often different. Seismic data is usually king in hydrocarbon exploration.
Right, those sound waves, they bounce off subsurface layers.
Precisely. AI algorithms analyze vast amounts of that seismic data alongside information from existing well logs, geological models, and other geophysical attributes. They use classification models, for instance, to categorize different subsurface areas as either likely or unlikely to contain hydrocarbons. Or regression models might predict the probability of hydrocarbon presence.
Helping to quantify the risk.
Exactly. It helps exploration companies assess the geological risks associated with drilling in a particular location and allows for much more strategic, data-driven, and ultimately cost-effective exploration campaigns.
Okay, and it's not just about valuable commodities like minerals or oil. What about arguably our most essential resource, water, specifically groundwater? How is AI helping us to better understand and manage that?
Forecasting groundwater availability is absolutely crucial, especially with increasing demands and climate change impacts. It's vital for sustainable water management.
Definitely.
So AI models are being developed to predict future groundwater levels. They do this by analyzing historical data on water table fluctuations, estimates of how quickly rainfall recharges the aquifers, various climate variables like precipitation and temperature trends, and even land use patterns, which can affect recharge and extraction rates.
So it learns from the past and present to predict the future water levels.
That's the goal.
Yeah.
This kind of predictive information is incredibly important for water resource managers, for planning sustainable rates of groundwater pumping, for allocating water for agriculture effectively, and ultimately for ensuring a reliable, long-term water supply for communities.
We've talked a lot about supervised learning, where the AI learns from data that's already nicely labeled or has known outcomes. But what happens when we don't have that kind of labeled data? Maybe we just have a huge pile of measurements and we suspect there are patterns, but we don't know what they are yet. That's where unsupervised learning comes in, right?
Exactly. Unsupervised learning is fascinating because it allows the AI to find inherent structures and patterns within the data itself without any pre-existing labels telling it what to look for.
The AI discovers the patterns on its own.
In essence, yes. One key application in geology is using it for what's called lithofacies classification, basically identifying different rock types based on measurements. We use clustering algorithms. Common ones are k-means or hierarchical clustering.
Okay, clustering. Grouping similar things together.
Precisely. These algorithms take, say, we'll log data, those continuous measurements down a borehole, and they group the data points based on the natural similarities in their measured properties, like density, resistivity, gamma ray signature. The result is distinct clusters that often correspond directly to different rock types or lithophases, even if a geologist hasn't explicitly gone through and labeled every section beforehand.
So the AI is basically finding these natural groupings within the data that reflect different geological depositional environments or rock formations. That seems like a really powerful capability for initial exploration.
It absolutely is. It can quickly give you a first-pass interpretation of the subsurface geology from raw measurement data.
What other kinds of hidden patterns is unsupervised learning helping geologists discover?
Another really interesting application is in identifying structural patterns using something called self-organizing maps, or ISOMs. Yeah, they're a type of neural network, particularly good at visualizing high-dimensional data. Geologists might feed them thousands of orientation measurements taken from geological structures like faults, fractures, or tilted bedding planes. The SMM then organizes this data, revealing underlying patterns and distinct structural domains, areas where the structures have a consistent orientation.
So it helps see the bigger picture of how the rocks have been deformed.
Exactly. It aids geologists in their interpretations of the tectonic history of a region, understanding how the Earth's crust has been folded, faulted, and deformed over potentially millions of years. It can uncover large-scale structural trends that might not be obvious just by looking at individual measurements.
That's like uncovering the sort of invisible architecture of the Earth's crust. What about using unsupervised learning to maybe detect unusual chemical signatures in geological data, perhaps pointing towards mineral deposits?
Yes, definitely. Density-based spatial clustering, often known by the acronym DBS-SCAN, is a great example of an algorithm used for this.
DBS-SCAN.
Okay. It's particularly good at finding clusters of varying shapes and also identifying outlier points that don't belong to any cluster. In geochemistry, you might apply DBS-SCAN to data from soil or rock chip samples measuring various element concentrations. It can group together samples that are spatially close and have similar, maybe anomalously high chemical characteristics.
So it finds hotspots of weird chemistry.
Basically, yes. It can identify these geochemical anomalies that might be indicative of underlying mineralization processes. The clusters represent areas with potentially elevated concentrations, and the outliers might also be significant. It helps pinpoint exploration targets by highlighting these unusual chemical fingerprints in the landscape.
It really seems like unsupervised learning is like having an AI geologist who can just sift through raw data and spot subtle clues or groupings that we might not even have known to look for beforehand.
That's a very good way to put it. It excels at discovery from unlabeled data.
Now, let's maybe move on to what many consider the really advanced frontier, deep learning. We touched on CNNs and RNNs earlier, but how is deep learning more broadly taking geological analysis to an even higher level of sophistication?
Yeah, deep learning, characterized by those very complex, multi-layered neural networks, really enables much more sophisticated types of analysis, often getting closer to human-level perception on certain tasks. We mentioned convolutional neural networks, CNNs, already for image interpretation.
Right, the rock photos and satellite images.
Exactly. Their power there is immense. In geoscience, they're used routinely now to automatically extract geological features from satellite and aerial imagery, mapping fault lines, identifying different types of land cover, finding surface expressions related to mineral deposits. But they're also being applied at the microscale, too. Analyzing microscopic images of rock-thin sections or core samples. Deep learning models can automate large parts of petrography, the detailed description and classification of rocks based on their mineral composition and texture. This can significantly speed up data acquisition compared to manual analysis by a geologist looking through a microscope.
So CNNs are like these super-powered eyes that work from satellite scale right down to the microscopic, automatically identifying geological features in images. That's impressive. What about analyzing data that inherently changes over time, like seismic waves from earthquakes or maybe the signals related to ongoing volcanic activity?
That's the domain where recurrent neural networks, or RNNs, and related architectures like LSTMs really shine. They are specifically designed to handle sequential data where the order matters.
Data that comes in a stream.
Exactly. In geology, RNNs are used quite effectively to interpret seismic waveforms for the detection and classification of earthquakes, distinguishing them from other seismic noise like mine blasts or storms.
All right.
They can also be used to model dynamic geological processes that evolve over time. Think about modeling patterns of sedimentation in a basin. tracking the subtle ground deformation signals that might precede a volcanic eruption, or even modeling the slow, long-term movements of tectonic plates.
Trying to understand processes unfolding through time.
Precisely. And this ability to model time series data is also crucial for improving predictions of time-dependent geological hazards, like forecasting landslide likelihood based on rainfall patterns or predicting flood extents based on river flow data.
It's almost like giving the AI a memory, allowing it to understand how geological processes unfold sequentially. What about the absolutely massive amounts of seismic data we collect specifically to image the Earth's subsurface for resource exploration or hazard assessment? How is deep learning revolutionizing that specific field?
Deep learning is making truly significant advancements in seismic data processing and interpretation. It's a huge area of research and application. For starters, it's being used to dramatically improve noise reduction in raw seismic data.
Cleaning up the signal.
Exactly. Seismic data is often incredibly noisy, and deep learning models can be trained to very effectively separate the useful geological signal from unwanted noise, making the underlying structures much clearer.
Okay, that's fundamental.
It is. Deep learning is also significantly enhancing the automated detection of key subsurface features, like faults and fractures, directly from the seismic volumes. Identifying these discontinuities is crucial for understanding fluid flow pathways, potential drilling hazards, and the overall structural framework.
Finding the breaks in the rock.
Right. And perhaps most excitingly, deep learning techniques are being applied to boost the actual resolution of the subsurface images we generate from seismic data, a process called seismic inversion or imaging. This gives us a much clearer, sharper, more detailed picture of the complex geology hidden deep beneath our feet.
So deep learning is essentially helping us see deeper, more clearly, and more accurately into the Earth's hidden layers by processing that complex seismic data more effectively than ever before.
That summarizes it well, yes.
Now, let's maybe take a step back again and look at the really big picture, literally. How is AI being integrated with remote sensing technologies and geospatial analysis to give us this comprehensive synoptic view of our planet from above?
Yeah, the synergy between AI and remote sensing is incredibly powerful. It's transforming how we monitor and analyze the Earth from space and from the air. AI algorithms are becoming standard tools for advanced image processing tasks on remote sensing data.
Like what kind of tasks?
Things like automatically detecting specific objects within satellite or aerial imagery, maybe identifying individual buildings in a city, tracking specific types of vegetation change, or counting certain animal populations from high-resolution images. Also, classifying different types of land cover across vast areas, and very importantly, detecting changes in the landscape over time by comparing images from different dates.
So AI is helping us automatically keep track of things like deforestation, urban sprawl, the retreat of glaciers, or the impact of natural disasters, all using satellite or aerial data.
Exactly. It automates analysis that would be incredibly time-consuming or even impossible to do manually at large scales.
What about the more specifically geological applications of interpreting satellite imagery with AI? We touched on mineral exploration.
Right. Beyond mineral exploration, where AI analyzes spectral signatures to find alteration zones, AI is enabling much more accurate and efficient interpretation for other geological purposes too. It's used to create highly detailed maps of different land cover and land use types, which is fundamental for environmental management. It helps monitor geological changes like coastal erosion rates, desertification, or the dynamics of glaciers and ice sheets, key indicators of climate change.
Seeing the Earth change in near real time?
Pretty much. It provides a continuous monitoring capability that's unprecedented.
It really sounds like AI is unlocking a whole new level of valuable information from these massive archives of satellite and aerial imagery. How does all this then tie into the geographic information systems, the GIS platforms, that geologists and environmental scientists use every day?
GIS is essentially the framework, the platform, for integrating, managing, analyzing, and visualizing all sorts of spatial data, including remote sensing imagery. AI significantly enhances what you can do within a GIS environment.
How so?
It improves the analytical capabilities. AI tools can be integrated into GIS workflows to perform more sophisticated spatial data analysis. It makes it easier to combine and analyze diverse types of geospatial information, maybe layering geological maps with population density, infrastructure networks, and environmental sensitivity data. And importantly, it boosts the accuracy and sophistication of predictive modeling within the GIS environment.
So you can build better predictive maps inside the GIS.
Exactly. This has a huge range of applications, conducting more accurate environmental impact assessments for proposed projects, developing better strategies for natural resource management, optimizing urban planning and infrastructure development based on geological constraints and opportunities. AI makes GIS an even more powerful tool for understanding and managing our planet spatially.
Okay, so AI is amplifying the power of GIS. Let's talk about some of those really critical applications in environmental monitoring and especially assessing and maybe predicting natural hazards. Where is AI making the biggest difference there?
This is an area of intense research and growing application. In earthquake prediction research, for instance, while true prediction remains elusive, AI algorithms are being used to analyze massive amounts of historical and real-time seismic data, searching for subtle precursory patterns that might, potentially, indicate an increased likelihood of a large earthquake in the near future. It's about finding statistical precursors.
Improving forecasting, if not exact prediction.
Exactly. For mapping areas susceptible to landslides, AI models are very effective. They integrate data on factors like slope angle, rock or soil type, rainfall patterns, vegetation cover, and proximity to faults or roads to create detailed landslide susceptibility maps, identifying high-risk zones.
Helping planners know where not to build.
Precisely. Similarly, in flood risk assessment, AI analyzes historical flood data, river gauge measurements, rainfall forecasts, and terrain models to predict potential flooding extents and depths with increasing accuracy, supporting early warning systems and evacuation planning.
Okay.
And more broadly, AI is being applied in numerous ways to studies of climate change impacts. Analyzing climate model outputs, tracking changes in ice sheets and sea levels from satellite data, understanding impacts on ecosystems, AI is becoming an indispensable tool for grappling with the complexities of our changing planet and its geological systems.
This has been an absolutely fascinating deep dive into the literally world-changing ways AI is transforming geology. Just to quickly recap some of the most impactful insights for you, the learner listening in. It's truly remarkable how AI is stepping in to automate dangerous or difficult tasks.
The robotics and automation part.
Right. And its incredible ability to identify these hidden patterns in enormous data sets, patterns humans simply can't process on their own. And, of course, the profound implications this all has for how we manage our planet's finite resources and how we try to predict and mitigate potentially devastating natural disasters.
Yeah, I think the key takeaway for you really is that AI in geology isn't just some niche academic technology anymore. It represents a truly fundamental shift in how we observe, analyze, and understand our Earth.
It's a paradigm shift.
It really is. And these advancements have very direct, real-world consequences for the future availability of essential resources, for our safety and resilience in the face of geological hazards, and just for our fundamental understanding of the incredibly complex and dynamic processes that shape our home planet.
Absolutely. And on that powerful note, here's maybe a final thought for you to consider as we wrap up. As AI continues its incredibly rapid development, maybe even in ways we can't foresee, how might entirely new types of geological insights emerge? Insights we can't even conceive of today.
That's a deep question.
Could AI one day maybe help us predict geological events, earthquakes, eruptions with such unprecedented accuracy that it fundamentally changes how we live on and interact with our dynamic planet? It's a truly exciting, maybe slightly daunting intersection of technology and earth science, and one that will undoubtedly continue to evolve and surprise us.
No doubt about it. The future's unfolding quickly.
Thanks so much for joining us on this deep dive.